Hello and welcome to today's PIR live event brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Today we have a panel of 3 guests. So first we have Dr. Luisa Trejos, who is an assistant professor in the Department of Electrical and Computer Engineering at Western University. I'll let you give a wave there and a hello so that it switches to you.
Hello everyone.
And next we have Dr. Tricia Breen Carmichael, Associate Professor in the Department of Chemistry and Biochemistry at the University of Windsor.
Hi everyone.
And Dr. Simon Rondeau-Gagné, Assistant Professor also in the Department of Chemistry and Biochemistry at the University of Windsor.
Hi, thanks for having me.
So I'm so glad to have all of you. Thank you for joining us. First, we're going to learn a bit about each guest's research in turn, and then we will have ample time for questions and answers following that. Remember that you can ask questions anytime, however. You don't have to wait for the Q&A to begin. You click chat in the top left-hand corner of your screen and type out your question, making sure that you switch the to field to all panelists and attendees. And if you include your name, your school, or your city, we'll be sure to give you a shout out when I ask your question. So that is enough from me. I think we should turn it over to our guests now, and we are going to begin with Dr. Trejos from Western University.
Thank you so much. And I'm going to just start by sharing my screen and getting my presentation going. Okay. There we go. Excellent. It's my pleasure to be here today so that I can talk to you about the research that we are doing on the development of wearable devices at Western University. My work focuses on the development of mechatronic devices for rehabilitation. And don't worry, I'm going to explain what that means. You're probably familiar with some wearable devices that have been around for a long time, like headphones for listening to music or headsets for playing virtual reality games. But when we think about wearable devices these days, we usually think about those that use sensors of some kind to measure things about your body. For example, the Fitbit can track how many steps you take each day, how many hours you sleep, or some of them can actually measure how fast your heart beats. What we are looking to do is to build on these technologies and develop wearable devices that can not only measure things, but that can actually help a person move a part of their body. So I just want to start by showing you a prototype that was developed in my lab, which is the Wearable Biomechatronics Laboratory, or the WearMe Lab, and this is called the WearMe Brace. And you can see it in this video that it's actually bending and extending the elbow of the person that is wearing it. And this is the device that is called a mechatronic device. So I want to explain what mechatronics is a little bit before moving forward. Mechatronic systems are composed of 4 main areas. So first we have the mechanical system itself. So for example, the parts that support the arm, how many joints it has, what material it's made of, how far does it bend, and things like that. We also have the electrical system, which includes the sensors and the actuators. And the actuators are, for example, motors or things that provide movement. We then have the computer system, which is the computer hardware, so the physical components of the computer. And finally, we have the control system, which is the software or the set of instructions that the machine would actually have to follow. And it's a combination of all 4 that define mechatronics as we know it today. So you can think of mechatronic systems as smart machines or machines that can automatically respond to what is happening in the environment. So what we wish to do is to design mechatronic systems that allow us to provide rehabilitation to people that have had some kind of injury. So for example, a sprained ankle or a broken arm. The best way to fully recover from any kind of injury is to see a therapist who will give you a series of exercises to do so that your muscles become strong again. If you've ever injured yourself and have had to do rehabilitation, you would know that these exercises are not always easy to do. And most importantly, it's very easy to not do them. Nobody's really supervising you, so why not getting away with not doing them, right? Well, the issue is that then you don't really recover and you end up with pain that does not go away. So the idea is to develop mechatronic devices that can track if you are doing your exercises, that can help you do them correctly, and that can tell you if you are improving. They could also send you information to your therapist to let them know how things are going, or they could interface with the game so that you are playing a game as you're doing your exercises. To develop these devices, the most important wearable sensors that we need is one that can measure muscle activity, as you can see in this video. You can see here how the lights on these little devices are turning on as the student moves their arm, which indicates that there's activity being detected. The signals that we get from these sensors are not that easy to use, but if we combine them with other information, for example, motion information, we can then use them to control a device. So you can see how that is done in this other video. So the wearable device is actually sitting here on the table, and there's a foam arm that is attached to it. Because this device is still under development, we don't want to actually mount it on a person because we don't know if it's going to be entirely safe. So what we do is that we mount it on the table, but the person still has these little sensors that are attached to the muscle so that we can measure the activity of the muscle. What is shown here at the top right are the signals that we get from the sensors. And you can see how those signals are then being processed by the computer that you can sort of see in the background. They're going into the mechatronic system, so they're being used to control the device so that the device can literally follow the movement that the person has. The advantage of this is that if she were to not be able to fully lift her arm because the muscles are weak, then the device could take over and do it for her. Or if the device detected that she's not doing the exercises correctly, it could correct her movement to ensure that she is doing them right. Now, the problem with this device is that it's really too large, too heavy, too bulky. Imagine what it would be like to carry this thing on your arm all day. No, thank you. So part of the work we are focusing on is trying to make these devices smaller. And for that, we are looking to use what we call smart materials. And I think you'll hear more about this from some of the other presenters. These are materials that can change their shape when electricity passes through them. As you can see here in this video, the cable here is basically contracting when the electricity passes through. And this is what is called a twisted coil actuator. And it behaves very similarly to our own muscles. And the idea is to use these twisted coils to develop wearable devices, for example, for hand rehabilitation, where the coils form cables that can help move each finger individually. One problem that we currently have is that they get very hot. So we are still working on ways to isolate the heat, but still allow them to cool properly. One more thing that is really important is to develop these devices so that they fit each person according to their size and according to the type of injury that they have. For that, we recently acquired a 3D printer that allows us to print hard and soft plastics at the same time. And we are currently designing wearable braces that are comfortable to wear and very light. There is still lots of research to do before we can get to the point of using these devices on people, but we hope to end up with devices that are small and light, that are also very smart in how they behave so that they can help people recover faster from their injuries. And thank you so much, and I look forward to hearing your questions later.
Well, thank you so much. That's installment 1 of 3 of our presentation. So we're next going to move to Dr. Tricia Breen Carmichael at the University of Windsor.
Hey, thank you. I'm going to start just by sharing my slides. There we go. So I'm going to talk to you a little bit about our research. I'm a materials chemist, and I work in the area of stretchable and wearable electronics. And this area is really exciting science. And it's kind of interesting to think about how it got started. So it might surprise you to hear that wearable electronics actually started more than 50 years ago. That was when the first idea came out. And this idea was the idea of Hugo Gernsback, who was an inventor, and he was a science fiction pioneer, and he was always inventing things. And so this idea was a television you could wear actually on your face. And so you would strap this across your eyes and be able to watch your favorite TV shows. Of course, the problem is, it's not very wearable. It's not very comfortable to wear. And it took a really long time before we had the technology to actually make it better. So if we look at what happened next, we started to have better technology. So we had things like smartphones. So this Google Cardboard here is a smartphone that you put in literally a cardboard box and you put it on your face and it gives you a virtual reality experience. So a little bit better than TV. And so then we can improve on that more, and we can have, for example, this wearable display, this virtual reality system that looks a little bit nicer than a cardboard box. So in my lab, we try to think about what's next. How can we make these devices more wearable? And that's really what I want to talk about today. How can we make these devices so that you don't notice you're wearing them? It's not a big, heavy, bulky thing that's strapped to your body. So wouldn't it be better if, for example, the wearable display or the virtual reality system could be a contact lens that you can actually, it would be soft enough that you could put it in your eye and actually have this virtual reality experience right from your own body almost. So another example that we can think about are other wearables and what they could become. How can we make these wearables even more wearable? So most people are familiar with the Fitbit, of course, and Dr. Trejos talked about this. You put it on your wrist and it tells you how many steps you've taken and your heart rate. But wouldn't it be nice if it wasn't so bulky and it wasn't something that you noticed you were wearing? So if it could be, for example, a very thin film of a device that actually was laminated directly on your skin, so that you could interact with it simply by rubbing your finger across your skin, like this prototype over here on the top right. There are a lot of exciting opportunities for wearable electronics in the medical field. So an example of today's electronics, if you have a problem with your heart, you might have to go and get an electrocardiogram. And this is a case where you have electrodes and they're put on the top of your skin, but then they're connected to these wires and they go to a monitor. And if you need to have a lot of data collected, you might have to walk around with this Holter monitor, which is kind of a box that you have to carry around with you, maybe for a week. So in the future, what's next? How can we make this more wearable? And that's shown in the bottom right here. What you see here is something called the Heart Sock. And it is actually a soft device that's molded to the surface of a heart. And this is a beating heart in this video. And what it's doing is it's monitoring the heart function in real time. And it can be implanted actually inside the body. So something that would be so, you wouldn't notice that you had it on at all. Here's another example of a virtual reality type of technology. This is a glove that's on the hand at the top here. And what it's doing is every time the person moves their hand, the glove is mapping how they're moving it and then recreating it in virtual reality on the computer. So this device is bulky. You wouldn't really want to wear this for too long. And so what we ask is, wouldn't it be better if that device was soft, more like a glove, that you could just put on your hand and it would detect what your hand was doing and how it was moving? So maybe the device on the bottom, which is made out of kind of a rubbery material, would be something that you could just slip on and not really notice that you're wearing it. So all of the examples that I've shown are today's technologies and kind of where we would like to take them. And they all have something in common. They all are based on soft materials. And the reason we think this is the future for wearables is that if we're going to have electronics on our bodies or even in our bodies, then our bodies are soft. And the electronics should be soft too, so that we don't notice we're wearing them. So the types of materials that my group looks at to try to make electronically functional are all soft materials. So we might work with soft rubbery material, like a silicone rubber that you could just laminate on your skin. It could be something like a rubber glove. You've seen, if you go to the doctor's office or the dentist's office, they wear these rubber gloves. What if those could actually do something electronically functional, like mapping the location of your hand in space? And then the last material is just our clothing. We all wear clothes. They're made out of fabrics. Can we integrate electronics directly into fabrics so well that you wouldn't even notice you were wearing them. You'd put your socks on in the morning, and your socks would be telling you how many steps you took or what your heart rate is, and you wouldn't notice it at all. So that's really what our goal of what my research program really tries to focus on. So the question is, how do you make this electrical? How do you take these different materials and make them into computer systems or displays or things like that? And that's really the heart of what my research program looks at. So we have to think about the type of materials we need. So if you took your smartphone or your iPad and you opened it up, and I don't recommend you do this, but if you did, you would see all kinds of materials inside that are rigid, they don't bend, they don't stretch, they're definitely not soft. So the big research goal is, how do we take those materials and integrate them with these soft materials so that we can make a functional system that works and can stretch and bend and is soft like the human body. So here's an example. If you did open up your iPhone, you would see metals. All electronic devices need conductors. We have wiring in our houses, we have wiring in our phones, we have wiring in our computers. So everything needs a conductive material, and metals are the best conductors. Metals don't stretch though, right? So if we have a block of gold, it's not stretchable and it's not soft. If we have copper wire, it's the same. What we do in my group is we can take these materials and we can integrate them with soft rubbery materials and make them stretchable. And so we have a lot of different methods that we use to do that. But in the end, what we have is a piece of rubber that has a metal film on it. This one in the middle is gold, the two top ones are gold, and then the bottom one is a copper one that's been patterned. And these will stay conductive as you stretch them so that we could build devices from them. So let me show you, what can we do with just stretchable metals, just as something as simple as that. So here are some examples of what you can do with stretchable metals, and these are all examples from my lab. One thing you can do is you can build a strain sensor. So in the upper left, we have a sensor that's on my graduate student's thumb, and every time she bends her thumb, you see the LED lights light up, indicating the thumb is being bent, and every time she straightens it, the lights go out. So this is a motion detector. It monitors human motion. Over here we have electronic fabric. So this is an image that we took with a microscope of a piece of fabric that we've integrated metal into the fibers of the fabric. So you can see in the middle here, all of the tiny fibers that twist together to make the yarn of this fabric are coated with metal. So this is a conductive pathway in the fabric, and so we can make wearable, truly wearable devices using this kind of new material. And then finally, in the bottom right, we have an ordinary glove, the kind we wear in the lab. In this case, what we did was we were able to deposit metal on the surface of the glove. And right now in my lab, we're working on building a glove like this that's easy to wear and can be used to map the motion of the hand in virtual reality. So we really are trying to do a virtual reality glove that's highly wearable. So my last example is beyond metals, what can we do? Everybody likes things that light up, and there are a lot of great wearables where you have devices that emit light. So in the upper left, you can see this one here. This is a glove. You can buy these. They have lights embedded in the fabric, and if you're out riding your bike, you can use that as a turn signal. So if you do a hand motion, you can activate the lights, and it starts to flash, and you can let cars know if you're turning left or right while you're out on your bike. But if you look a little closer at this device, so in the bottom left, you can see that there's a lot of hardware that goes with this kind of simple thing. We have a circuit board, we have some wires that have to go through the fabric, and so it becomes more bulky and harder to wear. So in my group, we're looking at how do we make really stretchable and wearable light-emitting devices that could one day be displays, wearable displays. So on the right side, you can see pictures from my lab where we've taken rubber and we've integrated it with a light-emitting material. And now what we can do is we can have stretchable light-emitting devices and displays. So ultimately, these are things that could be worn on the body as displays or signage or whatever you want. So I'll just finish up. Our view of wearable electronics is that the future is going to be soft. It's going to be soft like our bodies, and we're going to be having wearables that you won't notice that you're wearing them. And you know, this field started 50 years ago. I can't even imagine what it's going to be like when you're all grown up. and your adults, what kinds of things you're going to be wearing. I think it's going to be amazing. And so there's lots of exciting scientific problems to work on. And I just want to finish up by showing you, these are my students. They're the ones who build all these things and do all this work. So if you come to university, even when you're an undergraduate and you're fresh into university, you can work in a lab and you can build things like this. Right away, you can start to contribute to research and science and technology. So they're all actually as happy as they look. They love working in this field, and they have a lot of fun. So I'm going to conclude now, and I will look forward to your questions.
Thank you so much for that. And for showing the real live people that are part of your team too. I think sometimes we forget that there's a whole team that works in the lab with you. So with that, I'm going to turn it over to Dr. Simon Rondeau-Gagné.
Thank you very much. So let me just share my presentation as well. All right, so thank you for having me. It's a real pleasure to also discuss about what we're doing here in the Department of Chemistry at Windsor University. So I think the first two presenters really show like how promising is the field of wearables and how creative and imaginative the people are when they're thinking about new type of wearable devices. So in my group, we're chemists. So we are focusing on the materials that we're gonna use to build up these new devices, these new wearables. So today, I'm just gonna try to show you a little bit what's our approach to develop these new materials. So our main goal is to develop the materials for the next generation of electronic devices, which a little bit like what Dr. Carmichael mentioned, will be totally entirely made of wearable devices. So there's a lot of different things that you can think about when you're thinking about wearables. You can treat a bunch of different problems if you wear some devices on your body, but also we are thinking that in the future, these little devices will be stretchable, will be soft, and they can be put also inside the body. And as you see here on the little picture, there's a bunch of different problems that you can cure if you think about putting some implants into your body. You can cure some smelling problems, some eye visions problems, some hearing problems. So we're really trying to tackle these problems and then develop new materials for new type of devices. So I'm a big superhero fan. So if I can just put an image on that, imagine Iron Man that has this super nice armor that give him a bunch of different superpower. But our goal is to take that rigid armor and basically put it directly on Iron Man's body. So he will not have to wear his huge armor, heavy, but have already his body made entirely of this armor. And our inspiration in my group is definitely the most impressive and the most interesting materials, the human skin. So you might have never thought about it, but your skin is actually really impressive. That's a really stretchable materials. It's extremely resistant to strain. Just think about when you're having a little problem on your skin. If you move all day long, it's not gonna be worse. It's gonna maintain its size. So there's no deformation. It's really robust. And also the most interesting thing when you think about wearables, skin is self-healing, so it can regenerate itself. So that's something we're really intrigued, and we would like to put this or to include these new properties in the next generation of wearable devices. So all our challenge are basically we're trying to develop skin-like materials. And how we do it? Well, we use the most known type of materials, plastics. So plastics are used everywhere. You're surrounded by plastics. Cars are made of plastics, water bottles, toys, even your clothing is made of plastics. So a lot of people knows how to prepare these plastics, but maybe you never thought about using the plastics as smart materials. And our plastics, so our type of materials we're working in my group, they are more closely related to inks. So inks, they are full of different colors, but we can really tune their color depending on their molecular structure. So depending on the atoms inside the polymer or inside the materials, we can tune their properties. So if you think about it, you can tune the properties of your inks, and then you can design different type of materials with different properties. So if you think about wearable, then you would like to get these inks, for example, to be more stretchable and to be soft. And the nice thing about inks is that you can use inkjet printing to just pattern it. So our goal is to develop the materials for the next generation of devices, but we would like to create these devices by printing. So you can just go on your computer, has the inkjet printer to print you a pressure sensor, And then at the end, you will have something that you can put on your body that will be stretchable, that will be wearable, and that will also sense the pressure that you wanted to sense at the first place. So that's really the methodology and the approach we are using. We are really trying to get to these new type of inks. And how we do it? Well, we're chemists, so we're using chemistry. And I don't want to go into much details, but basically, chemistry is like cooking. So if you like cooking, then you might probably like to do some chemistry experiments as well. So we are actually trying to combine a bunch of different elements into our recipe to control the properties of the final materials we're trying to develop. And basically, depending on the type of inks we want to develop, depending on the stretchability we want to have, depending on the final devices we want to build, we're just going to change some elements, and we're going to end up with a total different molecule and materials. In my group, as I said, we're trying to develop these new materials for the next generation of wearables. There's really two important parameters or properties we're trying to engineer in our materials. And the first one is stretchability. If you think about having wearable devices on your body, during the day, you're going to move. You're going to have a lot of movement. There's a lot of different things surrounding you that will force the device to be stretched at different strain, at different percentage. So we really want to engineer our materials to be more stretchable. And since I really like superheroes, I would say that our final goal is to get as stretchable as Mr. Fantastic. So if our materials could be that stretchable, then we can think about designing a brand new type of devices that will be entirely stretchable for a lot of different applications. The second property we're trying to get in our materials is self-healing, as I said when I was starting to talk. Basically, if our materials could not only be stretchable, but also could repair themselves, first, it would be much more convenient if you have any damage to your devices, but also you can have a much longer time of, you can utilize it for a much longer time. And just to give you a little example, so this rubber here was cut in two, put back together, and then if we apply a strain, you see here, you can actually stretch the materials even more than it was originally. So self-healing in materials is something real, something that we can think about when we're going to design the next generation of electronic devices. And in terms of chemistry, really simplified the approach that we're using. We are actually trying to develop new materials by improving their connection. So if you think about materials as a spider web, for example, if you apply strain to this spider web, you're just going to break it apart. But if we can put some little connection between the spider web fibers and we apply strain, then instead of breaking the whole spider web, we're just going to break down these little connections. So our materials in general will be much more stretchable. And our role as chemists is just to investigate these little connections and see how we can improve them. There's another approach that we can use. We can blend something that is totally not stretchable with a stretchable matrix. So overall, the film that will be the mixture of the stretchable and the non-stretchable materials will be stretchable. So these are two approaches that we're trying to use in my group to develop these new materials. And I think you had a lot of good examples of what's the future of wearables. Just to give you my own favorite examples, I would say. We can think about developing new camera that could be directly put inside your eyes. We can think about flexible batteries, so you can wear your solar cell, for example, or your batteries on your body that can be the power supply for any type of cell phone or any other application. And at the end, I think, to get back to my Iron Man example, that would be really nice if we can develop the electronics directly on the skin. And for that, we'll need our materials, and that's where we're trying to get, and we are focusing our research on. So let me just finish by showing you the people who are actually doing the cooking and the chemistry. So these people are, they had no clue about how to improve materials, and then slowly they're getting a lot of knowledge about it. So all this work and all this approach has been done by these people, and I'll be really happy to answer all your questions. Thank you.
Thank you so much. 3 great presentations. I know we saw lots and lots of great examples that are going to come back to us, I think, in a lot of questions. So I am just going to make sure everyone is unmuted here, and then we'll get started. We have a few questions already in queue. Please keep them coming. If you're watching right now, then we'd love to hear your questions as well. Don't forget to send them to all panelists and attendees if you can, and to include where the question's coming from so that we can give you a shout out when we ask your question. So let's start off with a question for Dr. Carmichael from Ms. Goulet's class in Bragg Creek, Alberta. They were asking, would this kind of technology be useful in extreme environments such as underwater or space?
That's a great question because it's something I'm really interested in working on too. The materials that we use we're really thinking for everyday kind of usage, but we need special materials for extreme environments. So instead of some of the soft materials that I talked about, we've been working on inventing new soft materials that are waterproof. So I have a research program where we make stretchable waterproof devices. So it's all about the materials, and I guess that's my answer. If you want to create something for a particular environment, what we do is we think about, what are the parameters we have to work with, and then we think about what kind of material can solve the problem, and that's really material science in a nutshell.
Great. And Dr. Trejos, we have a question from Alexandra in Mrs. Gummer's grade 4 class at Hillcrest. She wanted to know if you know of any applications in NASA or with the Canadian Space Agency using wearable devices.
I'm not 100% sure that there are lots of wearables being used. I do know that they would use them to make sure that the signals from the astronauts are good, like if they track their temperature and their heart rate. Those would have been things that have always been done since we started sending astronauts to space. I'm sure I can think of a lot of applications, but I am not 100% sure what they're using right now.
Great. And I think we'll go now to a question for Dr. Rondeau-Gagné from Liz in Hamilton, Ontario. She was asking, what material have you found that behaves most like skin?
That's a really good question. So for now, we're trying to develop these materials. I would say the closest one that we're using for now is made of rubber. So rubber is really soft, looks like skin. We don't have the self-healing behavior of skin so far, but actually in terms of stretchability, we're not that far. And since I was expecting to show, I'm a big fan of examples, so I have here, I don't know if it's gonna be clear, but you actually see that this material is really soft. So in terms of flexibility, it's really good, but we just need to get the self-healing properties to get it finally to be looking more like skin. But it's made of rubber.
And the material you did show that had sort of self-healing properties, did you had to take the two pieces and put them together, and then did they react? Were they different compounds, or what was that about?
So it's one material having some little connection inside the material. So it's all the same. It's just that if you break these connections, they're gonna be break apart, and if you put it back together, if you put the two pieces together, these connections will be reformed, so you'll have your healing. But it's all, overall, it's the same materials. You just need to get these connections together.
So were they just colored to sort of indicate the two halves?
Yeah, it was just more obvious.
Oh, okay. And I think we'll go now to a question for Dr. Carmichael from Shazib, who's a grade 5 or 6 student at Lincoln Alexander. And the question is, have doctors implanted any of the heart socks onto a living patient yet? So you showed us that sort of layer over top of a beating live heart.
So if by living you mean human, the answer is no. To be able to do that kind of experiment on humans, it's a long process, right? Because it has to be safe. We can't take chances with people. What you saw, I think, was a rabbit heart. So the rabbit was still alive, the heart was beating, the surgery was done. The way that the heart sock was made, though, which is kind of an interesting thing, they scanned the rabbit's heart and 3D printed the heart sock. So it was a perfect fit for that particular heart. So with that kind of personalization, it is the sort of thing that could be done in people, but these processes are always really, really slow. We need to make sure that it's safe, and a lot of approvals have to be done before we get to that point.
Excellent. That is still exciting that we've already gotten to the point where a living heart, animal or human, that it already had that wearable tech. let's go back to Dr. Rondeau-Gagné. Colin in the grade 4 class in Campbellford, Ontario, would like to know if there was ever a wearable device you wanted to create that utilized resources that were too difficult to get or use. And this question might be one that applies to everyone on our panel. So maybe we'll start with you, Dr. Rondeau-Gagné.
Yeah, that's really hard because we are actually investigating. So for most of the devices we would like to create, for example, these bioimplants and then these epidermal electronics, so the tattoo. We always wanted to create some, but we really need to get to the properties I just mentioned, which is the self-healing and the stretchability. So we need the materials, and that's really what we're trying to tackle. So in terms of devices, I cannot name any specific one because actually I would like to create all with our materials. Yeah, sorry not to be more clear about the answer, but that's really the question here.
Okay, maybe Dr. Trejos next.
Yes, I think in my case has been trying to find motors or any kind of actuation device that is small and light. So motors tend to be fairly heavy and bulky. And so finding small ones that still have enough power to lift an arm, for example, are very difficult to find. So that's why we started looking into the smart materials. And then in the smart materials, it has actually been quite difficult to source some of the materials that we need. So we're developing other actuators that are using electroactive polymers, which are just some sort of plastic, and finding companies that supply the various materials that we need to create those has been very difficult. But we have struggled with it, but we found a solution now.
Excellent. And what about you, Dr. Carmichael? Is there anything that you've wanted to create, but you couldn't get your raw materials for it?
Absolutely. It's one of the things about doing research is it's sort of this long process of problem solving. So when we wanted to make the stretchable light emitting devices I showed, we had a good idea for making the material that emits light to be able to make that stretchable. But the problem we had was we couldn't test it, because we needed stretchable electrodes and we needed stretchable transparent materials. We needed things that didn't exist yet. And so it was a little bit frustrating. And so what we did was we had to invent those things too. So it made the project take longer, but sometimes that's what you have to do to be able to test your ideas and to do the science you want to do. So we expanded our view of materials and took on a bunch of side projects so that we could build the device.
Excellent. I figured you would each have an answer for that one, something you wanted to do that you couldn't quite get the materials for. I want to go back to Dr. Trejos at Western with a question from Courtney at Lincoln Alexander. She wanted to know how much does it cost to acquire the supplies like the electronics and other materials that you need to create the arm that helps rehabilitation?
So it's actually about $1,200 to $1,500 to create that one. The motors themselves with the drivers are about $500 to $600. The sensing system is another $400 to $500 if you get some of the less expensive one. And then building it all together would put it probably at the $1,500 range.
So not inexpensive then.
No.
Let's see what other questions we have here. Trying to keep up with these questions thanks to our audience. There are lots and lots coming in. I'll get to as many as I can. Let's go back to Dr. Carmichael at Windsor. Would the motion sensor that you showed with your graduate student's thumb, would it be used for people who have disabilities?
I think it could be. What that device does is it detects how much mobility you have. So I think that if you were maybe doing rehabilitation exercises trying to improve mobility, then that wearable device could tell you how successful you are in real time. You could wear it while you were doing your exercises and see if you're seeing improvements. So that kind of a wearable sensor, I think it has a lot of different applications. It's a great question.
Excellent. And we're going to move to Mateo, who has a question, I think, for Dr. Rondeau-Gagné. How long does the average wearable rubber stretch? So maybe perhaps in a percentage might be,
yeah, that might
or
be.
how many times?
So I can answer in terms of percentage. So with the most efficient materials we've developed so far, we can go up to 500%. So if you have something that is really, if you have something about 1 centimeter, you can stretch it to 500 centimeters, which is really, really long. But that's for really specific and really expensive materials. So we're trying to get our materials to be maybe slightly less stretchable, but at least a bit more easy to produce and to fabricate.
Excellent, thank you. Next I have, I suppose, I'm not sure who would jump in for this question. I'm thinking maybe Dr. Trejos or Dr. Carmichael, but in Mrs. Goulet's class, they're wondering about the diagnostic or monitoring potential for this type of wearable technology. For example, in detecting an allergic reaction, monitoring blood pressure, or a diabetic crash. Is that kind of application close to being usable? Maybe we'll start with Dr. Trejos, if you have any insight on this area.
Yeah, so I'm very familiar with wearable devices that can monitor blood pressure. We are working on a couple of projects where we're trying to come up with better sensors because the existing ones are not quite where we would like them to be. In terms of recognizing allergic reactions or diabetic crashes, those are more chemical reactions that are happening in the body. So I am not familiar, Dr. Carmichael may know more about those. But in terms of diagnostic devices for musculoskeletal injuries, so injuries that require rehabilitation of some kind, there's definitely lots of devices that we can use to identify what is the type of injury that the person has just by looking at their range of motion and how the different muscles contract. So we're definitely headed in that direction.
What do you think, Dr. Carmichael? Any chemistry or biochemistry information to weigh in with there?
For sure. I think that there are devices now that can detect chemical things with the body from just wearing on the skin and monitoring sweat, the content, the chemistry of your sweat. There are also contact lenses being developed that you can put in your eye that will monitor glucose levels. So that's, of course, related to diabetes and things like that. So people are really wanting to develop these kind of wearables for that real time. You know, you want to be able to measure your blood sugar if you have diabetes. It would be good to have that data all the time. You don't have to stick your finger and then go and measure it. So you could, always know when it's time to have an insulin shot or something like that. There are wearables for this and pumps and things like that. But, to make it more wearable, this contact lens is a really, really exciting thing that's being developed.
Lovely. Well, I'm looking at the clock here and I'm seeing that we are just about out of time. Perhaps we can go sort of once around through our panel. If you have any nuggets of wisdom you want to share, any last words, anything exciting for our audience today. Let's maybe go in reverse. So we made Dr. Rondeau-Gagné wait a long time at the beginning there. Why don't you start us off?
Yeah, so maybe I would just conclude by going back to the last question. So I think these technologies are really close to be used. When I was a student, so when I was starting, I used and I developed with a research team a patch that you can put on your wrist to monitor the blood pressure. I heard some examples where also you can put these little wearable devices, put it in the body, and it can help to regenerate people who got some blood, spinal cord injuries. So there, I think the technology is there. We're still investigating, developing new materials. We want to always be more efficient, but I think in the next decade, that's realistic to think that we're gonna have more and more of these wearable devices coming on the market and in our own life.
Thank you. What about you, Dr. Carmichael?
So what I want to, I guess my parting idea is there's a lot of science going on in wearable electronics, and it's quite broad. So if you like chemistry, you can do chemistry. If you like engineering, you can do all kinds of different engineering. If you like biology, you can be involved. If you like physics, any kind of science is going to be applicable to this field. And so I think there are a lot of opportunities for students as they grow and go into university programs. There are a lot of opportunities to work on stuff like this, and it's really an accessible field for everybody to contribute to. So if it's something you're interested in, it's certainly available through whatever your particular interest is. This can be a field that you work in.
That's good to know. I think it's hard to realize how much collaboration really does go on, and the multidisciplinary ways that everything seems to be done now, especially research. So last but certainly not least, Dr. Trejos at Western University. I'll give you your chance here as well.
Very similar to what Dr. Carmichael said. It is just so exciting, everything that's coming up in this field. There is so much opportunity for doing research and developing new technologies. And I really do hope that some of the students that are participating here do consider studying something that allows them to contribute to the field by developing new technologies, because we really do need a lot of people working on it to get to the point where we can use them every day and they're helping people throughout the world.
Well, thank you so much to all three of our panelists for joining today and taking the time to tell us all about what they're doing in their labs and where this technology is headed, and answering our questions. We had some great questions from the audience. Thanks to everyone who joined us live today. That is all the time we have. Next up on PIR live event, just let you know, we are talking about math and the zombie apocalypse, among other things. More information on this and other PIR live event webinars can be found at pirweb.org. So thanks again for tuning in, and we'll see you next time.